So we were using Taylor series to write down the value to expand the row and the time changes, and we were taking only the linear terms and ignoring the higher order terms. And so we achieved an equation in which there was a variation of row with respect to time, and of course the variation of in the x, y, z direction of row. Now if I try to write down the earlier terms that we calculated in the vector form, then we observe that the vector del, which is written here, and sometimes the vector sign is indicated by a bar on the top, and another time, sometime we do it this. It's the same thing. They are equivalent notation. And we know from the knowledge of our vector calculus that del operator is identically equal to delta x by d by partial derivative with respect to dx times the unit vector I. Similarly, partial derivative of y times the unit vector j, and the similar term in the third z direction when we are talking about the three-dimensional space. And this in a shorter form can be written as the total derivative d by dt is equal to partial derivative of time plus v times v, the velocity vector, times del. And then if I use it to write down the equations that we obtain, then for example the derivative of temperature, if here I write any other variable, if it is f or g or h, we can write that, but we want to take from a physical quantity, and therefore temperature, which in fluid mechanics or fluid flow situation plays an important role, because due to friction or due to other parameters that are playing role in the fluid flow, the temperature changes, and therefore it has an importance. And therefore if I want to take the differentiation of temperature T with respect to the time T, then it can be written as the sum of these two terms. The first term is called the local derivative, and while this term is known as convective derivative. And when we expand it in the expanded form, it is written as the sum of these four terms as indicated. A simpler way of writing the total derivative is as follows. We write simply d of rho, and that is equal to partial derivative of rho with respect to times dt, that is the local derivative into time dt, and similarly with respect to x, y, and z. And this can also be written as d rho by dt, that is we are dividing throughout by time. So when we divide this by dt, then you can see that this cancels out. So here there is no differentiation with respect to total derivative d appearing. But here it will be d by dt, this is the same dy by dt, and this is dz by dt, resulting in these equations. And as we know, dx by dt is the velocity component u, dy by dt is the velocity component v, and dz dt is the velocity component w. The above equations show that small d rho by dt and the capital D rho by dt, that is the material derivative and the total derivative, they are having the same meaning and they are equivalent. And the later form, that is this form, is used simply to emphasize the physical meaning that it consists of local derivative as well as convective derivatives. The terms appearing on the right side is summation. We saw there were 4 quantities, and there were local terms, what we call as local differentiation, and also the other terms that are known as convective terms. Then we come to see what is the divergence of velocity, and sometimes we write down divergence of velocity as this: del dot v is known as divergence of quantity. The quantity on the right hand side of the equations can be written in this form, as we will discuss later, and that reflects that term is known as divergence of velocity. So we will consider in detail later.